Sorry, the students give slides. They can't see you, but they can see your slides.
Okay, that's unfortunately I'll have to work with that, right?
And hopefully they'll be coming over soon to fix
Okay, so in that case, I'm just going to work off the slides. I'm not going to use the board today, right? But okay, but just going back, what happens with the number of bases greater than the number of dimensions are combination first, unless I use sparse. And then when I use some additional criteria, like the shortest representation of the sparse, it's not just sparse. When we're using pseudo inverse, we've got a unique representation, right? Or one figure unique representation. We wanted the shortest representation. So that gives a unique answer. When we use sparsity, the vector will get a unique answer. Right? And assuming I can do this, I can keep increasing the number of bases, right? Because I have an extra criterion for uniqueness. So the shortest S or sparseness. In that case, what is the largest number of bases we can use? Let's assume sparsity. What is the largest number of bases you can have? The number of? Why do we say that? That's a good answer. Right. So here's what is going to happen. Going from one end to the other. If I have my data X and I keep increasing the number of bases. So those of you on Zoom, I'm drawing a figure where my X matrix X is as wide as Y, and my matrix P is as wide as X itself, and my matrix W is diagonal, and I'm going to write X equals BW. And you will agree with me that it's a unique representation, right? And so this may be equal to X or some scaling of X, right? And W can be a diagonal matrix. This has a sparsity of 1 also, right? And for given bases, the number of dimensions that we is unique. So what are the limitations when we're beginning to find bases in a given data set? If you want a unique representation without sparsity, then the number of bases is limited by the dimensionality of the base, right? If you are willing to consider sparsity as a criterion for uniqueness, to introduce uniqueness, you can increase the number of bases. That's going to give you what we call frames. And the limit there is when every data instance by itself is bases. And we're going to say there are some instances. Does that make sense? The two extremes when we increase the representation. So I'm going back here. What is the second case really saying? We're looking for representation. We want to be able to compose our data, right? So if instead of bases, I had a dictionary of all possible data, a matrix that included every possible data vector as the column, the weights vector simply selects the correct data instance, right? And then W is a one sparse vector, which means every element is every weight has only one non-zero element, correct? It's actually a one hot vector also because the one non-zero element is 1. So you're saying W, the zero norm of W is 1, and the one norm of W is also 1, right? So is this making sense? This is the limit of representation, your data itself. Remember, I'm trying to communicate things to you. In one case, I said, here are our bases, and this data instance is 73.2, right? In the second set, I think here's our entire data set. I'm sending you vector number frequencies. Both are going to be in frequency, right? So that's the history. If I throw in a bunch of extra stuff on top of my data vectors, now it becomes redundant, right? And again, the representation will become non-unique. So the limiting representation where there is no doubt whatsoever as to what I am sending you is where you use the data itself as a dictionary, right? It's simply to understand the data can get overlapped. And that means I have solved the problem of communication. Communication in the first place is simply sending you the entire data, right? One bother. So infeasible to construct such a dictionary. In the limit, you can require infinite entries, and our W vector is going to be infinitely large, or even if it is sending an index, you're going to require an offset this to send that index. So this is not going to be useful for representing data outside of your training sets, right? Because say if we both seen a million data vectors, let's send you a million data vectors. Then I get you want to communicate something that's not in my million. Is there an index I can send? There isn't an index I can send. It's not in my database, right? So what is the so how does that work? The problem here is that it's infeasible to construct a perfect dictionary, potentially infinite entries. So I want to go back and say, can I construct a smaller finite dictionary such that all data can be approximately tracked by one of these? Right? So giving you 1 million data instances, I'm only going to give you 1,000 vectors. But and so anytime I want to communicate a data instance, it is going to give you the index of one of those 1,000 vectors, but errors is the smallest possible. Right? So this is like saying, there's a bunch of common cases. And the next guy you came in, he looks a lot like the seventh case in the data set. Or the vector X looks a lot like that, right? You have to answer two questions. What do we mean by looks like? There are many different definitions. And what do we mean by? And how do you construct such a dictionary? So what do we mean by what looks like? You can have different data metrics, right? You can have different error metrics, and different error metrics will result in different solutions. So that generally represent the error as some divergence, right? And what we are saying is that any vector is now being composed as a entry from the dictionary, correct? But when I'm composing it as an entry from the dictionary, I can still write it as a linear decomposition. I can put all of my dictionary entries by vector matrix B, and I can say any data vector is going to be approximated as B times W, with the constraint that, for the constraint of W, sounds good. And what else? What is the second constraint? Speak up, I can't hear you. So the constraint on W is that the zero norm is 1. Only one entry is non-zero. And the one norm is 1. The one non-zero entry is 1, right? So this is still a linear decomposition. I'm approximating my vector as D times W. That's a linear decomposition. The constraint on W is a one-hot vector, right? And now you want to learn the dictionary B and the representation W for every vector such that the error is minimized, right? Which means you want to minimize the error between the original vector F and the composition DW. That's done in this manner. That making sense to everybody? And so, how do you construct this dictionary? How do you construct a dictionary that minimizes the error for every possible data vector? Now you can look at the map. I have the collection of data vectors in the notation coordinate B. Okay? These are the data which for the dictionary is being composed. B is the dictionary, is the matrix of data vectors. And W is the set of one-hot vectors, one per vector, right? And so one per B. And now you want to, you're given B, you want to learn B and W, such that the error between B and DW is minimized, with the constraint that every column of W is bound. So you see how this is still a linear decomposition problem. It will not change anything. Okay. What are we talking about over here? We're looking at something like between value, right? But in this linear decomposition. Okay. So, and now I'm interested in learning the dictionary. And for the training set, I want to find the WH, right? So I want to find the D and the W such that DW jointly minimizes the error between D and DW. Everyone with me? This is a convex problem. It's a square error. This is a convex problem. Yes or no? Pardon me? How many of you think this is a convex problem? How many of you have no opinion? How many of you have no opinion about having no opinion? Because some of you are interested in not going to raise your hands. I think this is all of you your hands. How many of you think it's non-convex? What about the rest of you? Okay. You think it's a convex problem? Right? You think P or W is a constant, it becomes convex. Otherwise, why is it non-convex? That it's a quadratic, right? Quadratics are convex. So why is it non-convex? Pardon me? Yeah. So in DW, you will say it's convex, but here's the thing, it's not. Because we have a constraint on W. If every possible W are value solution. No. It's just spots in the space. You don't define convex range functions over spots in the space or lines in the space. This is not convex, although you're looking at a nice quadratic function. Everybody see why this is a non-convex problem, right? So can you solve it? Using some closed form solution? No. Not here, right? So then how would you do it? Iterative and it's constrained, you're going to need something like. Can somebody say that aloud? What do you need? Can you say it aloud? Everybody. Projected gradients, anybody? Say it aloud. Oh God, you guys are horrible. You can't even mumble, please. You should mumble, right? So, yeah. I'm trying to find a B. I'm only interested in finding the dictionary such that the error over the collection of data and synonyms, right? Now here, this is a error minimization problem, but then I can use a technical coordinate system. I can fix my D and find the W that minimizes the error. Then I can fix the W and find the D that minimizes the error. And every step is going to, what is the gender? Is never going to increase the error. So every step will at least make sure the error doesn't get worse, right? So that's how. And if this were convex, it's going to reduce, right? So here's what I will do. I'm first going to solve I'll fix the D's and solve for the W's. Then I'll fix the W's and solve for the D's, right? So if I fix the D's and solve for the W's, I'm going to find the minimum over W's for between D and DW. But I can do this vector by vector because every vector is independently composed of every other vector. So, which means I only have to solve this individually for each vector. I'm finding the W such that the error between D and DW is minimized. Yes, Wayne? Yes. Like this? There is no straddle. This is not complex, right? We're just looking at W which have only one mark.
Yeah, I mean, and the other restricted situation is radio.
This, I mean, eventually you're going to find a local meaning. There's no other guy there's no guy that is radio. It's a coordinate system. It's going to go to some local meaning. Right? Okay, so can somebody tell me how to solve this first step? I'm giving you a dictionary. I'm asking you to find the W such that the error between B and DW is minimized with the constraint that W is 1/2. How do you solve it? Can you speak up, please? Not the closest B to the vector, right? Whatever divergence metric you chosen, according to that, it is because W is 1/2 is literally saying select. Right? We're going to select the dictionary entry that's closest to the vector. Make sense? Right? So the first step is simply going to be finding the closest D to the vector. And then the second step, I've got all the W's, I'm going to find my dictionary D. And so this gives you the very well-known k-means algorithm, right? Because Now, how does the second step work? I'm giving you the W's, right? I'm asking you to find the dictionary V. If I give you the W's and ask you to find the dictionary V, what are the W's saying? All of these vectors came from this dictionary. All of these vectors came from this dictionary. It's clustering. Correct. And then you're finding the one entry within the cluster that gets cluster, which is although your k-means is just a coordinate descent algorithm for a constrained linear decomposition. Right? It's linear, but the objective is non-linear. The objective is non-convex. You're doing gradient coordinate descent and guaranteed to converge to something. And you don't need equidavit steps. The principle would hold regardless of that. Right? Everybody is. So, make sense? Make sense? Some enthusiastic. Okay. So this is the grouping V by the dictionary entries. So that's in clustering. Right. So for those of you who can't see the board, it's tiny bar the palm. Let's keep 3, 5, 10, 1005, 1005, and 1. Okay, Alex is done, so we're all done. Manohar, what's the answer to the first one? Forget your name. Yeah. True or false? Anish, third one. True or false? Theta. Right? Third one, yeah. True or false? Okay. So, and what about the last one? True or false? Speak up, please. True. She says true. All of them are true, right? Now, so we've just done the math. I'm not going to go writing a math for a while. Because I spent 40 minutes just trying to get this response, the 9-minute mark in my regular class. Right? So I'm going to skip over the rest of the k-means description because we all know k-means. I'll just skip to the end. But this is all about clustering, right? You want to find latent structure in the data, structure that's not immediately apparent from the observed data, but which, if known, helps us explain it better and makes predictions about it. And clustering methods attempt to extract such clusters from proximity. First level structure is basically lowest level structure and gives you representations, right? So this is a classic clustering problem, completely unsupervised. Where now the key thing is the divergence net, right? So clustering is going to determine the naturally occurring grouping of data instances. What is a naturally occurring grouping? It has to have low within cluster variance, compact clusters which are far apart, right? And high between cluster variability. So something like this. And so you want to find the groupings of data such that the things which you put in one group are all close together, that don't fall in the same cluster are hopefully far apart, but this depends on how you define those things. Can you find a different kind of clustering? Can you see a second kind of clustering over there? Yes or no? Yes. Can you say yes together, please? Thank you for once. Right? Which is the second one? Circles. What is the distance measure you would be using in that case? Distance from a center, right? So just change my distance metric, and I'm going to get a completely different grouping, right? So skip all of the fancy stuff, but one of the keyest, most important things that uses for clustering is not just to find structure, it's also for quantization. This is where quantization is the business of mapping things onto the closest dictionary entries that we spoke of, right? And this was the famous, the optimal technique for finding these dictionaries. Came into an interesting history. It has been reinvented a couple of times. And it was invented, was first proposed by McLean in the 60s. Then in the 80s, Linné, Russo, and Gray republished it, right? Something called it quantization. Because McLean said, I can cluster. And these guys said, hey, you know what? The point in the middle of the cluster, call it a representative and make it a dictionary, and then I can map these onto that dictionary. I call it quantization. And then they came up with the second thing, which is usually called vector quantization in the 80s. And then after that, a guy called Lloyd realized that if you can do this over a vector, you can do it over a scalar. And so this was exactly opposite to what you'd imagine it to be. So, but then this is a classic one, right? All of this data. You can find these clusters, you can find the centroids of the clusters, and you can map each point onto the closest centroid. So again, same thing, right? This is the dictionary-based representation. You're saying X equals DW, find the W, the corresponding D and P becomes the representative of X, and then I just have to communicate it. I just have to send you the index of the dictionary entry. And it has some interesting applications that they use for. Very often they use for instance. For example, this used to be the big thing many years ago before COVID. This was the second guy with a variant instance. Who was the first? Boston. Anyway, suppose I want to retrieve all music videos. How would you do it? Based only on what person? Pardon me?
Yes or no?
Classification. How would you do it? Clustering one. So here's what we did, right? We're going to use something called a bag of words representation. And you need some way of describing this video. So every video has a bunch of features in it, any frames in it, and each frame has a bunch of features in it. So the video ends up becoming a large collection of feature vectors. Things like set vectors, more set vectors are better than set vectors for videos. And so now we have this video, it has become a collection of vectors. Now, I can generate these things from a very large amount of video data. I can train a codebook of this kind. And then when I have the representative, I have the sequence of vectors in this video, I can just quantize every one of the vectors within the video. And then when I'm done quantizing it, I can find that 4 of the vectors got mapped onto this cluster, right? 18 went onto that cluster, and so on. This is going to tell you how many of the vectors, feature vectors that got into the video went into each of my clusters. Right? That I'm not using the word because that's not me. And those together will form a cluster. Right? And now, basically, for this, you need the feature representation to characterize your data and the clustering employed. Anyway, and the way you would do it is create this histogram for your video, and you create a simple histogram for every video in your collection, and then you can just look at the closeness method of the response. And lines of code works shockingly well. In fact, this was used for the longest time before deep learning techniques came up. So, very effective, right? Yeah. Question? So a video has many frames, right?
Yeah.
And you have something called SIF vectors, scale invariant feature transforms. And SIF computes a bunch of feature vectors from each image. So a single image is going to become a collection of vectors. And then a sequence of images is going to become a larger collection of vectors. That's what we do, right? We have more motion SIF vectors. Anyway, going back, we have to worry about the clustering criterion. This becomes important, right? and the cluster compactness criterion, where and the distance of a point from a cluster. These are the three things that we're going to have to consider. So for the compactness criterion, we have some distance-based measures. There are different things you can think of. The simplest thing is what is the total distance between all the points, right? It's very expensive to compute. The other one is what's the distance between the two farthest points in the cluster. Also expensive to compute because you have to identify the two farthest points. So a simpler thing is to say, what is the distance from the center? And this is what we use, but then this is not necessarily the best definition of the spread of the cluster, because we have the other velocity could be more effective and capture the shape of the cluster. These things are assuming some kind of spherical clusters. Or you can have some Minkowski, and the distance that you use can be an L2 divergence, Minkowski distance, what have you, right? And now, or you could even say, I'm going to compute a probability distribution on the data in the cluster. And so, now, the second thing is how far is the data point from a cluster? I have a cluster of data. I'm giving you a new data instance. I'm asking you how far this data instance is from the cluster. How do you compute it? It turns out there are many answers to this, right? I can say it's the distance from the center of the cluster. That's not necessarily the only way. I can say what is the closest point in the cluster is. Now, how close am I to the boundary of the cluster? And I can assign it to the cluster whose boundary is closest. Or I can say what is the farthest point, right? Which is going to give me some notion of compactness. Do I compactly fit into this cluster? And that's a completely different thing. Or I can say, I compute the probability distribution of the cluster. What is the likelihood of this data point on this probability? And if that is high, it belongs to the cluster. If it isn't, it doesn't, right? All of these different criteria also come in. You can even have something like this, where I can fit a regression to my data points and say, I have these clusters which are in different regressions, which line is it for? And this becomes, you can imagine I have a bunch of cluster like this, another cluster like this. Topologically, a data point may appear to be closer to the sky and fall on the sky, right? And so, depending on what you're looking for as a distance measure, you're going to choose a different cluster mapper. And so the optimal clustering actually ends up being a very expensive solution problem. When I said we're looking at E equals Z, then asked if it's a convex problem, and I said it was not. It's not. Not only is it not a convex problem, it's actually a combinatorial optimization problem. Because the W is supposed to be 1 because they're sparse. Which means if I give you n data points and ask you to find out the best way of clustering these data points, then the one and only way of finding the optimal, guaranteed way of finding the optimal clustering is to consider every possible way of clustering the data. So if I have n data instances and I'm clustering them into n clusters, the number of different combinations is given by the very interesting formula over there. I know there's a -1 raised to something, but I promise you that number is never negative. It's a very large number. Right? So this is, I won't derive it, but then the only way to actually find the optimal cluster is to enumerate every possible way of clustering the data. Apply your compactness criteria. Again, every cluster has its own compactness criteria, right? And then say which one of these optimizes your, which one of these clusterings maximizes your clustering criteria, you choose that one. And clearly this is infeasible, which is why we get to coordinate this thing. That we look at the standard k-means, right? And for the standard k-means, we all know how it goes. Mechanically speaking, this is the whole process, but for specs. Okay, that's answer everybody. Now the answer the first question. False. And someone want to answer the second question. Right back there. Second one, what is the one? Fourth option, right? So the distance of a data instance from a cluster, there's no unique definition. Can be anything, right? And if you're trying to cluster based on regression, linear trends, you're going to use a regression model. Easy. And yes. Yes. So it's just going to be on the face of the picture, right? I'm going to skip the next few slides. This was just an interesting side point where we figured out how to cluster data using k-means, which was named by McQueen. Then we figured out that clustering actually allows you to quantify, and this became a major paper, the 20 years later, and then sometime later, this fellow Lloyd realized that if you scale that whole thing down to a scalar from a vector, then you can build an optimal quantizer of series. And we get a Lloyd max quantizer, right? So we have a sequence of slides. Just go over the slides. Now here, you know what quantization is. You get an analog signal, you're sampling it, you're going to quantize it, right? How do you quantize it? You typically want to quantize it to have the lowest possible error. And the simplest way to quantize it is to just form uniform bins, but this is not the most optimal way because highly probable samples have the same average error as very low probability samples. Whereas you want to make these bins non-uniformly wide so that things that are frequent have lesser error. And so you can actually have use the k-means algorithm to find this optimal quantizer. I'll skip that. And I have some slides on how the k-means clustering is performed. But again, you guys don't really need to know the details, right? The basic algorithm is you're going to find the distance from the data point from every vector. Then you're going to find the closest cluster. And then you're going to, this gives you a new cluster, and then the centroids for each cluster are formed as the average of all of the data points in the cluster. Now, this k-means algorithm, the classic k-means algorithm that I just mentioned, is making one assumption. What is that? It's making an assumption about the algorithm is not. What is that assumption? Right. You want the approximation and the signal you quantify in terms of the square root of the distance between. That will be the classic k-means algorithm. If you change the algorithm to something else, you end up with a different algorithm. It's still going to follow the same trend. It's still going to be coordinate descent. You can go back to my fifth slide and derive the solution for it, but the algorithm will be slightly different, right? But working with the L2 divergence is very convenient for reasons that you will see in a bit. I haven't gone through the because I know all of you might understand how to perform. Everyone to answer first question through the Lloyd max quantizer's training algorithm discussion case of k-means cluster. Now, what would we have to update to guarantee that the k-means approach would converge? We change from the L2 divergence to some other divergence. What would we have to update? The formula from the distance to the cluster, and is the centroid going to be the same? If we use a different divergence. No guarantee, right? And can convergence always be guaranteed? It's non-convex. You cannot guarantee this, right? But then the only thing, in fact, even this is going to be wrong, right? Sometimes I'm wrong. Anyway, let's go back to clustering problem. Everything that we did was based on alphabet. We never learned because it's locally convex. If I give you a cluster and ask you to find the point, such that the total square distance from that point from every data point within the cluster is minimized, that ends up in this number, right? So it's like the algorithms. But suppose I have these data, right? And I get the second kind of cluster using algorithms. You cannot, right? And so L2 divergence space clustering K-means will not find other forms of clusters. Here's the key piece of what they wanted to get to do. The central portion of today's lecture is going. The initial portion that is showing to the linear composition. Oops. This is something with you guys. Again, the second part is something that you all encountered, but let's go back and see. The way you would actually get the clusters that you want is by increasing the dimensionality of your data, right? So what I can do is put my data xy through some transform so that now it goes from 2 dimensions to 3 dimensions. Here, for example, I can add a z, which is going to be simply alpha times x squared plus y squared. And if alpha is large enough, now the data end up in a 4, right? Again, observe that the data are still 2-dimensional, even in the 3-dimensional space. But because the third component is a direct function of the first 2 components. Now, typically, the third component is a linear function of the first 2 components. It will end up in a hyperdimensional space, right? Because here the third component is a non-linear function of the first 2 components. You end up in a 2-dimensional circle that is curved. So the dimensionality of the surface on which your data lies is going to be the same as the dimensionality of the data. This surface can be out. Now, once I curve it this way, right? If I make alpha large enough, then I can make my bore big and steep. And now the height difference between the 2 circles is going to be large. And then if I just use regular K-means clustering, I'm going to get the first circle and the second circle. Make sense? Right? So the key is, and this is what is called kernel K-means. You're learning a kernel, you're putting it through a kernel function. You are transforming the data into a synthetic higher dimensional space, where the desired patterns become natural clusters based on Euclidean distance and distance. Right? The problem is, what is the sum? Here's an example with this. But more generally, what function do I use to go from my 2-dimension from my lower dimensional space to higher dimensional space? That's not clear. And secondly, you have this problem of distances in higher dimensional space. I've gone from 2 dimensions to 200 dimensions. Now, instead of just computing a Euclidean distance with 4 terms, I'm going to have 200 square terms. That's not a very useful thing for me to be dealing with, right? So the issue is that we want to transform the data through some possibly unknown function, phi of x, into a higher and just to get potentially infinite dimensional space, such that I can now perform clustering, and now instead of defining the distance in the original space, I'm going to be defining my distance in my higher dimensional space. I'm going to be between phi of x1 and phi of x2. And I'm going to be performing clustering in the higher dimensional space. Okay. But then here's the thing. This is still just a function of x1 and x2, right? I haven't added new information. I have not added any new variables. The extra dimension that have been arrived at by manipulations of x1 and x2. In fact, all of the dimensions of this manipulation are x1 and x2. So it has gone from x to phi of x. So the Euclidean distance between phi of x1 and phi of x2 It's still just a function of x1 and x2. That makes sense to everybody? Or the puzzle. That makes sense to you? Really, right? Okay. I'm going the two diametrically opposite combinations, yes. We can actually have functions, kernel functions, which continue up to infinite dimension. There are other problems that we cannot have. Right, so we're not putting any restriction on how high the dimensionality must be before you begin getting the structure that you want. Right? So now this gives me something. I don't need to explicitly go into that higher dimensional space to compute the distance. That's the magic, right? Look at the distance in some, look at the Euclidean distance between Z1 and Z2. The Euclidean distance between Z1 and Z2 is Z1 minus Z2 whole square. So Z1 minus Z2 transpose and Z1 comes in polynomials, which is Z1 Z1 plus Z2 Z2 minus 3 times Z1. Right, straight up. So if I go up to higher dimensions, it's going to be the same thing. I went from phi x to phi of x. So the distance is going to be phi x1 plus phi x2 minus 2 times phi x1 phi x2. Right? Here's the thing. If I know how to compute this inner product in the higher dimensional space, without actually going into the higher dimensional space, then I can compute this distance without explicitly going into the higher dimensional space. You see that? Makes sense to you? Yes, no? No? So, where's my sword? Obviously, everybody's missing my sword. That's why I don't get it understand. But look at this. If I want to compute the Euclidean distance between Z1 and Z2, that's just the norm of Z1, the square norm of Z1, plus the square norm of Z2 minus 2 times the inner product of Z1 and Z2. Right? Similarly, if I'm trying to compute the distance between phi x1 and phi x2, that's going to be the square norm of phi x1 plus the square norm of phi x2 minus 2 times the inner product of phi x1 and phi x2. This everybody agrees? Suppose I was able to compute this inner product without explicitly computing phi. Some magic function which computes phi x1 dot phi x2 without actually going into the higher dimensional space. Then just using that magic function, and that's it, a magic function is really right. So instead of going from my 3-dimensional space to 3,000 dimensional space and computing my Euclidean distance to 3,000 dimensional space, there's this other function which can compute the inner product between two vectors in the 3,000 dimensional space, but it requires much less computation, right? Then I can use that function to compute these three inner product terms. And then I can compute the distance in the 3,000 dimensional space. Make sense? Right? So we can use this trick. This function is called the kernel function. A kernel function is a function that can compute an inner product in a very high dimensional, some unknown dimensional space, without explicitly going into that dimensional space. Make sense? Right? And so, if I have a function of this kind, which can compute phi x1 dot phi x2, I can just use kx1 x1 plus kx2 x2 minus 2 times kx1 x2. That's going to give you the distance between phi x1 and phi x2 in that higher dimensional space. And now I can use the kernel function. Make sense to everybody? And so this is, but then what kind of function is a good kernel function? How do we compute that? It turns out there are many functions that are good kernel functions which compute the inner product in a higher dimensional space. Very often you can compute this inner product without even knowing what the function that takes you to the higher dimensional space is. All you know is that there is some nonlinear transform which is taking your data into a space with many much higher dimensions, and you're computing the inner product in that dimensional space, so you can compute the function. Right? So kx for these kernel functions k can compute this inner product without explicitly going into the higher dimensional space. And very often you want to know what the higher dimensional space is. So what kind of functions can act as such kind of functions? For that, we're going to look at some very simple properties of inner products, right? Take any vector V. What is, if V is a non-zero vector, what is the guarantee about the square norm? Is it just non-zero? It's going to be positive. It's non-zero. It's going to be positive, strictly positive, correct? So now, if I take a bunch of vectors and compute a linear combination, any linear combination of these vectors, is the result also a vector? Right? It is a vector. Correct? And what is the guarantee about the square norm of the resulting vector? Also positive, or if this linear combination ends up in a zero vector, it's non-negative. It doesn't depend on the weight state. Regardless of the weight state that I choose, it's going to have this property. Right? So, regardless of the A's I choose, I'm guaranteed that the square norm of U over here is non-negative. Put it here. I can just say the square norm of U is the summation of the linear combination of V transpose linear combination of V. It simply becomes the sum over all pairs of vectors in V and of the weighted sum. PRE times PRE. This is guaranteed. This has to be non-negative. And it should not matter which set of V's I take. It should not matter any set of V's. You give me any set of V's. You give me any collection of. Doesn't matter how large that set is. Doesn't matter which set of V's I choose. It doesn't matter which set of A's I choose. Regardless of the V's I choose and the A's I choose, this property is satisfied. Right? You agree? This is making sense to everyone, this condition. And so, if a kernel function is computing an inner product, this kernel function, I can stick the kernel function in instead of the inner product, right? If the kernel function is computing an inner product in higher dimensional space, you know that the same property must hold even in the higher dimensional space, right? Even in the higher dimensional space, regardless of the x's I choose, regardless of the a's I choose, this property must hold, right? Everybody with me? Ben? Right? Angad, making sense? You boys, making sense? Martin, making sense? Yeah. You guys on the outer regions. Makes sense, okay. And this, we said, is a kernel function. So if this property is satisfied by my kernel function, then it's actually computing in a high dimensional space. This is called Mercer's condition. And any function that satisfies this property is guaranteed to be computing in a product in a high dimensional space. You don't do it, and you're only looking at the kernel function. You may not even know what the space in which it is computing this inner product is. And so, as a corollary, because any kernel function that satisfies that property computes an inner product in a higher dimensional space, the flip side is that the distance between 2 points in the high dimensional space is a valid distance, right? And so, because it's still a distance, it must satisfy the property of the distance, which means that phi x1 plus phi x2 minus 2 times phi x1 phi x2 must satisfy the properties of distance because it's non-negative and should only be 0 if x1 equals x. Right? And so, extending kx1 x1 plus kx2 x2 minus 2 times kx1 x2 is guaranteed to be exactly a distance, and it's guaranteed to be non-negative. It will only be 0 if x1 equals x. This is a corollary. This falls out of the first property of first Mercer's property. Everybody with me? No. And so, and we also get the triangle property dxw plus dy is greater than or equal to dx. This is the standard property to given distance. Right? So this falls out. And now, what kinds of kernel functions have this property? We satisfy Mercer's condition. Here's a whole bunch, right? X transpose y plus c. That's a kernel function. but that's just computing it in Euclidean space. Ax transpose y plus c raised to n. That's a polynomial function. That function actually satisfies Nurse's condition. It turns out that activity function is actually computing the Euclidean inner product in high dimensional space. This one, Gaussian. This is a particularly interesting one. This is computing the inner product between x and y in an infinite dimensional space. Right? Where it's satisfying Nurse's condition. I can use this for to compute distances in this infinite dimensional space. And you'd think going to infinite dimensions really blows up things. Really doesn't, right? Or you have this exponential function. So there are many more. There are many kernel functions which satisfy this property. And for a while, back in the 90s and early 2000s, finding kernel functions was important in grad students who wanted to graduate to practically work. So, if I want to find these results, you can work it out. You can find it here. So, I'm not working it out because if I had 5 more minutes, but also the people out there can't see it. But yes, you can work it out. And so now I can use kernel k-means to perform the clustering out here, right? I'm going to do this in some high dimensional space. This is still just k-means, right? Nothing changed except I'm going to be computing the means in the high dimensional space, and I'm going to be compared, which could be, just the average or the average. But here's the problem. If I'm working with kernels, am I actually going into the high dimensional space? Yes or no? No, right? I'm just computing in a product in that space without going. I mean, imagine using the exponential kernel space. There's no way you're going to be storing an infinite dimensional mean for the cluster. So this, we will never actually be able to compute the mean of a cluster because you don't actually go into the infinite dimensional space. And so your k-means algorithm is solved. Now, once you begin working in the kernel space, earlier you could just find your centroid and store your dictionary, right? You can't do that anymore. How does that change? I'm going to find, firstly, the first step is finding the cluster, right? I'm going to find the point, which is the cluster which is closest to my point, which is going to say, find me the point cluster such that the distance between phi of x and the mean of the cluster is minimized. So the mean of the cluster is simply the average of phi of x's, right? In both cases. If I expand it out, I can write the whole in terms of inner products. And so I'm not actually explicitly computing the mean. I'm writing it out as the average of the high dimensional representation of every point in the cluster. I'm explicitly considering every point in the cluster. And now that's going to give me this result where this distance itself is going to be looking at inner products with a phi of x with every point in the cluster. And that's going to be written in terms of kernels again. Since I'm running out of time, I'm not going to do this formula, we can see this because the concept is very straightforward. And so what happens is that when you're computing the distance in the high dimensional space, you can do this using only kernels without actually going into the high dimensional space. But the expense that you have is that you're not just computing a distance from a centroid, you're computing the average inner products over all of the points in the center. Right? And in fact, this is you get some terms over here looking at the inner products between all of the points in the centroid itself. The second term can be computed once per cluster. There's this term, which is looking at the average of the kernel value of this distance point, of the current point from all of the points in the cluster. And the first term is the kernel of the function of itself, which is its inner product in the high dimension space, not in high dimension space. So many of these distances can actually be viewed as distances Euclidean distances in a higher dimensional space. So they all sort of map down to something very similar, right? And so here's how your kernel-based k-means in high-dimensional space will operate. You're going to initialize. Now, when you perform k-means, you initialize the centroids typically. So if you're working in this high-dimensional space, you have no centroid, right? You have to initialize the clusters. So these are my initial clusters. And then you'll be going through each of your data points. If you put, right, the centroids are virtual. You can't actually compute the centroids, right? For each data point, you're going to be finding the distance of the data point from each of these clusters. And to compute, this is to say, finding the distance of the data point from the virtual centroids of each of these clusters, it uses this ugly formula, which explicitly sums over all of the elements of the cluster. Right? And that's how you will be assigning data points to the clusters, and you have new clusters, right? And now you have new clusters, you'll be repeating here. You're not actually going to be computing centroids. So the business of computing centroids goes away, but the distance computation becomes very expensive. So this is the so-called kernel k-means. The trick of going up into high-dimensional spaces and performing linear operations to obtain effectively non-linear operations. And doing this without explicitly going into the higher dimensional space. That's something that's very common. In fact, a neural network is used when you thought of as kernel functions with this variance. Thoughts? Keep switching your names. You got to tell me when I mix you up, okay? Yeah, you outnumber me many to one. Thank you. So, only the second and third. Kernel methods transform the data linearly. No, they don't. They're not linear. They are high-dimensional. They are the Euclidean distance can uncover non-convex clusters. Whereas if you're working in the Euclidean space, you're going to get the clusters are always going to be convex. In the higher dimensional space, they're convex, right? And how many clusters? That's always a problem, right? How many clusters do you want to find? And so there are many techniques. One of them is to say, I have all of my data points. I can find my damn matrix of inner product, and now it's in the high dimensional space. You can perform an eigen decomposition of your damn matrix and find out how many significant eigenvalues you have. So that's what you do. Yes, for the number of clusters. There's a mathematical reasoning behind it. Okay? So this is sort of giving you an idea of how linear operations can still uncover very non-linear structure. And the simple solution, the key solution is to shift into high-dimensional space, but even that can be done through linear operations. After all, an inner product is just a linear operation. The only thing non-linear about the whole thing is the kernel function itself, right? But beyond that, everything else is the linear operation. So it means that all of the things we did, like ICA, like non-negative matrix activation, all of these could in principle be done in high-dimensional spaces, right? So there's a whole field of such methods called spectral methods, which attempt to find principal subspaces in high-dimensional kernel space. And clustering would be performed in these spaces, other things, other operations, but all of them are kind of analogous to kernel k-means. So we can stay there, right? Now, we have other kinds of clustering methods. which are not simple clusters in high-dimensional spaces. Something like this, right? If I want to find clusters for a certain of thing over here, I really want to find the lines. And then if you found standard domains, and so, or if I wanted to find clusters over here, the clusters are obviously that, but the trends are, if you ran k-means, you're not going to get these clusters. So again, knowing your data, you can apply regression, but then this is not actual things. This will not be even more advanced regression. So I'll stop there. Thank you for your time, and I will see you in the next class.